Hello, everyone. In this video, we are going to look at um, the complexity lower bound of comparison sorting algorithms. As you recall that we can use comparisons to sort n numbers. The first algorithm we looked at was insertion sort. So insertion sort is a quadratic time algorithm. And then we look at merge sort, we look at quick sort, randomized quick sort, and also we just look at heap sort. So all these sorting algorithms use comparisons to switch the orderings of two items. And as we know that the best situations we have seen from these sorting algorithms in terms of time complexity is in the order of n log n, big O of n log n. And insertion sort is slower, which is big O of n squared. So then the question is, can we come up with a sorting algorithm using comparisons to beat the big O of n log n time complexity? Okay, so let me first give you the answer, and then I'm going to prove why that is the case. So the answer is no. Okay, the answer is no, which means that if you only use comparisons to sort plus some other index mechanisms, but the primary operations are comparisons to figure out the ordering of two items, then you cannot beat the big O of n log n time algorithms. So that is the first lower bound result. So we call it the complexity lower bound because no matter how you come up with a sorting ideas, as long as you only use sorting, as long as you only use comparisons plus index mechanisms, it's not going to be better than the order of n log n. Okay, so now let's see why this is the case. So let me open up a whiteboard. Full screen. All right. So imagine I have an input, which is a list of n numbers. Okay, so imagine that I use comparisons. Okay, so comparisons then will compare two numbers, right? So for each time you choose two numbers to compare. So they will then end up a sorted list. Okay, so then let's say A prime is sorted. So if you think of this sorting algorithm, it's just one. So it's just a one pass using comparisons. So starting from A, and then you end up at sorted. So if you get, let me put A star here, and then if you get another A1, So different orders of these numbers, n numbers. And then let's say they are different order, but they are still in the same range of numbers. And then they are also sorted into A stars. Okay, so you have, in general, you could have n different permutations. I'm sorry, n factorial, many different permutations that they all end up in here, in A stars. And through comparison, so which means that I would think of if I use different comparisons, I should be able to, by choosing different numbers to compare, then from A star you should have all different permutations as in their leaves, right? So it's a so this is a one, so maybe it's A here, and then the other one is A star. So this algorithm will using different ways of ordering to generate all possible permutations of A star. So at the leaf level, you have n factorial many leaves. Okay, so comparison, you can then think of it as a binary tree because each step, this is a fixed algorithm. So each step you only compare two numbers, okay? But you can choose different numbers to compare, but you only compare two numbers. So it is a binary tree, right? So you compare with two numbers, depending on the result, you will either go this way or go the other way. So it's a binary tree with n factorial many leaves, and hence the height of it, obviously, when the tree is balanced, then the height is the shortest, and that is the best time complexity, or the number of comparisons you can make in order to sort. Okay, so it's a balanced, and you have n factorial many leaves, and so the height will be log n factorial. So that will be the best you can hope for. Is the best complexity we can hope for, and then it is actually achievable, as we have seen that merge sort, quick sort, and heap sort, they are all achievable n log n algorithm. So now let's see why log n factorial is in the order of n log n. So the easy way to look at is so there are two ways we can look at. Obviously, this is a great n factorial is greater than or equal to n to the n over 2. Okay, so you can so you could, for instance, in order to prove it, you could prove n factorial square is greater than or equal to n to the nth power. So then this is written as n times n minus 1 times 2 times 1. And then you multiply the other n factorial, but this time you change the order. So it becomes like this. Okay, so then you multiply each column. So what it end up is that we want to show that n minus k, okay, times k, or n minus k times k plus 1, or n minus k minus 1 times k. So let's do it this way. So k here is from 1 to n. So that's each column like this, right? So when k is equal to 1, then this n minus k minus 1 is, I'm sorry, plus 1. Yeah, n minus k plus 1. So when k is equal to 1, then this is equal to n, right? So that's this term. So what we need to do is that, so we have n columns, and then each column is this. We just need to do is that this is greater than n. So is this clear? Yeah, I would think so, right? So we can do it by mathematical induction. And when that's the easiest way. So when k is equal to 1, it's obviously true, then you would assume that when it is, so when it's a k is true, then we just need to say when k, for k plus 1, k plus 1, which is also true. So for k plus 1, then we can do a little simplification here. So this is, we want to use this, okay? And so what we need to do is, okay, so we, yeah, so here, this should be plus here. And also for this k, we only, so this k for this is, k should be just from 1 to less than n over 2, because when k is greater than n over 2, that will be in the same form as this. So we only fix my k from 1 to n over 2. Okay, so because when k is greater than n over 2, so they just switch the order. So that is the same thing. So now we can see why this is going to be, so this is going to be, so this thing is going to be greater than or equal to n. So we simplify this a little bit. So this is becomes n minus k plus 1 minus 1. And then this is a k plus 1. So we distribute this. So this becomes, for this part, and the second part is minus k plus 1. Okay, and then this is going to be n minus k plus 1k plus n minus k plus 1 minus k minus 1. So this part, by the induction hypothesis, is greater than or equal to n. And so what's remaining here is a plus n minus 2k. But since k is less than or equal to n over 2, so which means 2k is less than or equal to n, so minus 2k will be greater than or equal to minus n. So this is greater than equal to n. Okay, so each of this column is greater than or equal to n. You have n columns. Hence, what we're going to get is the n factorial square is greater than or equal to n to the nth power. And obviously, n factorial is less than, well, strictly less than. Well, when n is equal to 1, that's equal. So this is n to the nth power. So, so we get n factorial less than or equal to n to the nth power greater than or equal to n to the n over 2's power. So you take log. So it's between n log n and n log n half. So this is the, it's in the order, it's a zeta, right? N log n, big zeta. And we obviously, we can also use a Stirling formula, and that will also give you the same result, okay, in the order of a big zeta and log n. So this explains using comparisons to sort numbers, the best algorithm, the best algorithms in terms of efficiency we can get is in the order of n log n. And that is achievable because we have looked at merge sort, we have looked at quick sort, and also heap sort. So they are all in the order of n log n. Okay, so that is the end of this video. Thank you for watching.